Hi, Transitional Math students. Mrs. Robinson here to work practice benchmark chapter 4 with you. Chapter 4 is on powers and roots. We do exponents, little negative exponents. We do exponential notation. So let's look at the first problem. The first problem says an astronomer finds that the diameter of an asteroid, asteroid A, is roughly here, 10 to the negative 2 kilometer. Whereas the diameter of asteroid B is roughly 10 to the positive 5 kilometers. About how many times greater, or how many times as great is the diameter of asteroid B than asteroid A? So we're comparing these two. Let's look. If I have 10 to the negative 2 and I put this back into standard notation, the decimal is right here after the 10, and if it's to the negative power, I'm going to move in the negative direction to put it back into its standard notation. So I'm going to move it over 2 places, and that gives me 0.1. All right, and then let's look at 10 to the 5, the 5th power. Here's the decimal right here again, and if I put it back into standard notation, I'm going to move it in the positive direction 5 times. So I'm going to move it over 1, 2, 3, 4, 5. Every time I move it over, I need to add a 0. 1, 2, 3, 4, 5. So this will be 10, 0, 0, 0, 0, 0. And if we put our commas after every 3, we can see this is 1 million and this is 0.1. How many times greater is it? Well, you can just compare them like this. If I line up 0.1 with 1 and I move the decimal to where this decimal is, it moves over 1, 2, 3, 4, 5, 6, 7 times. It moves over 7 times. Or I can look, how do I get from this exponent to this exponent? From negative 2 to 5 is 7 times over. So about how many times as great is the diameter of asteroid B than asteroid A? 10 to the 7 times greater. This is 10 to the 7 times greater than asteroid A. All right, let's look at number 2. Which expression represents 1 over 5 to the 6 using a negative exponent? Remember, negative exponent basically looks like this. 1 over any number is equal to that number, we're using x to represent any number, to the negative first power. 1 over x is x to the negative first power. 1 over x squared equals x to the negative 2 power. That negative exponent just brings it to the denominator, okay? And you guys will learn a little bit later more about that. So using that, if I want to make this be a negative exponent, I just bring it to the numerator and change the exponent to a negative, 5 to the negative 6 power. And that will be c, 5 to the negative 6. Don't put the negative in front of the 5. This was not negative 5 to the negative 6, which would make this negative 5 to the negative 6 power. So that was not that. It's positive. All I do is bring this up and make this a negative exponent. So it's C. Let's go on to number 3. Which expression is equivalent to, and let me scroll this up a bit, which expression is equivalent to 7 cubed times 7 to the negative 4th? Now the rule for this is when you have the same base, these are both 7s, you simply add the exponents, whether it's a negative or a positive. You could look at this a couple different ways, and you could take this to the denominator and do a division problem. But why? They're the same base. You just add their exponents. So I'm going to go, this will be 7 to the 3 plus negative 4. 3 plus negative 4 is the same as 3 minus 4, which makes this 7 to the negative first. Now this has a negative exponent and none of my solutions do, so I'm going to change this back to what it looks like when it's in fraction form. When I have a negative exponent, I put it on the denominator. This is 1 over 7, which would be C. All right, on to number 4. A golf ball is dropped from the top of a cliff. After 6 seconds, the ball hits the ground. The distance in feet the ball traveled can be estimated like this. About how far did the ball drop? All they're asking me to do is multiply this out. There's a big problem to it. They just want to know how far did the ball drop? Well, the distance can be traveled can be estimated by this. So they're just saying, what is 3.2? And the parentheses means multiply times 6 squared. What is 3.2 times 6 squared? That's all this says. Well, go 6 squared. 6 times 6 is 36. So I'm going to go, what's 36 times 3.2? You can do that on a calculator. If I do 3.2 times 36, I'm going to get approximately 115.2. Actually, not approximately, exactly, and that was in feet, and that should be D. Okay, so just make sure you understand that parentheses means multiply there. Evaluate this, and they tell us A is 3 and B is 6. So if I have 8 cubed minus B squared, make sure you plug everything in correctly and be careful of double negatives, all right? So I'm going to plug in 3 for A, and 3 gets cubed. And then I'm going to subtract, and the subtraction's on the outside. Then B here was 6, so I make B be 6, so minus 6, and 6 gets squared. So I'm literally just plugging in 3 for A and 6 for B, and I've rewritten it. Now go ahead and perform the operations. Remember, please excuse my dear Aunt Sally. You do parentheses first, then exponents. Here I have both of these in parentheses. I'm going to do their exponent. So 3 cubed literally means 3 times 3 times 3. 3 times 3 is 9, 9 times 3 is 27. 3 cubed is 27, and I almost wrote 23, sorry, 27. And then I'm going to subtract off 6 squared. That's 6 times 6. I do this first before I do any kind of addition or subtraction. So first I do this multiplication, then I do the subtraction. So 6 times 6 is 36. So I'm going to go 27 minus 36, and that will give me negative 9, and that's D. And that is a 9. I know, it doesn't look like a 9. All right, which expression is equivalent to negative 3 times negative 3 times negative 3 times negative 3? This is repeated multiplication, which is what the exponent gives you. This is just going to be negative 3, and there's 4 times, so to the 4th power. Make sure this is all in parentheses, negative 3 to the 4th power. That is not the same thing as negative 3 to the 4th power, okay? This is on the outside of the parentheses. So what this would make me do is I would have to do my exponents first, then I'd multiply by this negative, or negative 1. So this would be 3 to the 4th power, and 3 to the 4th power is 81. And then I would multiply it by a negative, which would give me negative 81. Here, this is 3 times 3, which is 9, times 3 times 3, which is 9. A negative times a negative is a positive. A negative times a negative is a positive. So I'm going to have 9 times 9. This would give me positive 81, and this would give me negative 81. So be careful. If the 3 is on the outside of the parentheses, it's not the same as when it's on the inside, especially when you have an even exponent. So make sure you write it correctly. This is negative 3 to the 4th power. All right, on to 7. What is the value of 5? K to the negative 4th if K is negative 2. Careful of all these negatives, all right? So I'm going to plug in negative 2 where there's a K. 5, and where there's a K, and anytime I have a negative, I would like to do a parentheses. So this is in my parentheses, that was K, and I'm taking that to the negative 4th power. So when I do that, this means 5 times negative 2 to the negative 4th. Now remember, I do my exponents first, and then I do my multiplying. Please excuse my dear Aunt Sally. Parentheses and exponents go before multiplying and dividing or adding and subtracting. So make sure you do this first before you do this. So negative 2 to the negative 4th. Well, that's kind of confusing. This negative power makes it hard. It's not just to the 4th where I just go negative 3 times negative 3 times negative 3. It's to the negative 4th. So what I'm going to do is I'm going to put this on the denominator. This is going to be 5 times, let's change this to the denominator. This will be 1 over negative 2 to the 4th power. Now I have a positive exponent. By taking this to the denominator, I've made this positive. Remember, x to the any power to the negative 4th power is just 1 over x to the positive 4th power. Okay, And that's how I can get rid of that negative exponent. So here we have no more negative exponents. So I'm going to do 1 over negative 2 to the 4th power. Well, negative 2 to the 4th power would be negative 2 times negative 2 times negative 2 times negative 2, 4 times. Well, negative 2 times negative 2 is positive 4. Do these. Negative 2 times negative 2 is positive 4. 4 times 4 is 16. So this denominator is actually 16. So rewrite this. This is going to be 5 times 1 over 16. Now go ahead and multiply this. 5 times 1 over 16. 5 is the same as 5 over 1 times 1 over 16. Multiply across the top and across the bottom. 5 times 1 is 5. 1 times 16 is 16. And you have 5 over 16, which is C. Okay, guys, on to number 8. Number 8 says, find the cube root of 512. Okay, in order to find your cube roots, I want you to know some of your basic perfect cubes. You can also do this for perfect squares. So just write the first 10 or 12 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's just write till 12. There's our first 12 numbers. If I cube 1, that's 1 times 1 times 1, that's just 1. So 1's a perfect cube, a perfect square, perfect everything. 2 cubed would be 2 times 2 times 2, which is 8. 3 cubed is 3 times 3 times 3, which is 27. 4 cubed, 4 times 4 times 4, 64. So here's my first 4 perfect cubes. 1, 8, 27, 64. So if I cube root 27, I get 3. If I cube root 64, I get 4. Let's do the perfect cube of 5. 5 times 5 times 5 is 125. 6 times 6 times 6 is 216. And then 7 times 7 times 7 is 343. 8 times 8 times 8 is 512. 9 times 9 times 9 is 729. I'm getting away from my numbers here. 10 times 10 times 10, that's easy. You just have a 10 and 3 zeros. Okay. When you cube 10, the number of zeros is the number of powers. 11 times 11 times 11 is 1331. And then 12 times 12 times 12 is 1728. So just kind of being familiar with these perfect cubes helps you. And this one gave you a cube root of 512. If you're kind of aware, oh, that is a perfect cube. 512 is the perfect cube for 8. So if I take the cube root of 512, I get 8. Now, if you have a calculator that does cube roots, a lot of calculators will do cube roots. You're just going to go second cube root and then type in 512 and cube root it, and you'll get 8. All right, number 9. Which expression is equivalent to the product of m to the negative 4 times m? That's a negative exponent, so you can bring it to the bottom and make it 1 over m to the 4th. But why? Same base, add exponents. Well, the exponent there isn't written. If nothing's written, it's to the first power. M to the 4th is the same, or excuse me, m to the negative 4th times m just m is the same thing as m to the first power. So I have the same base, I just add my exponents. So I'm going to go m to the negative 4 plus 1, and then negative 4 plus 1 is negative 3. M to the negative 3. Now that's not one of my choices, so I'm going to go ahead and get rid of the negative exponent and change it back into a fraction. So to bring this to the denominator, it becomes a positive exponent, 1 over m cubed, and it's a. Remember the rule, x to the negative 1 is equal to 1 over x. 1 over x is equal to x to the negative 1. Okay, so remember, I can change to a positive exponent or a negative exponent by using that rule every time. Okay, let's do number 10. Which expression is equivalent to b to the 4th? So I want b to the 4th here. And I have b over 8 divided by b over 4. I have all of these. So let's go through this. This one is 4 times b over b to the 5th. Well, this doesn't have an exponent, so it's b to the 1st. So I'm going to use the rule. If I have the same base, let's say b to the 1st over b to the 5th, If I have the same base and I'm doing division, I subtract exponents. So same base, b, subtract exponents, 1 minus 5. So 1 minus 5 equals b to the negative 4th. And then I have this 4 here. Okay, that 4 stays on the numerator. So this would be 4, and then I have my same base. I subtracted the exponents, so I still have a 4 here. I still have a 4 here. So this would be 4 times b to the negative 4th. Now the 4 is not in parentheses, so I'm not taking the 4 to the negative 4th power. Oh no, I'm only taking the b to the negative 4th power. So that would be 4 stays on the numerator. To make this a positive exponent, you take it down to the bottom, b to the 4th. So this is 4 over b to the 4th. That's what I get here. 4 over b to the 4th. That is not b to the 4th. Nope. How about this one? Same base, subtract exponents. So it's going to be b to the 8 minus, it's a negative exponent, so it's a double negative here. Double negatives turn to positives. So I'm going to get b to the 12th. That's not. All right, how about this? Same base, subtract exponents. B to the 16 minus 4 also gives me b to the 12th. Nope, it must be this one. Same base, subtract exponents. B to the 8 minus 4 is b to the 4th. So it is A. It's A. So remember that rule. When you're doing division and you have the same base, you subtract exponents. Okay, and this 4 can be left out. It's a multiply, so as long as you're multiplying everything at the end, you'd still subtract exponents, and then you multiply by that constant at the end. All right, let's go ahead and go down to 11. The average weight of an African elephant is this, 1.44 times 10 to the 4th pounds. It's a big weight. And that of a white rhinoceros is 7.94 times 10 to the 3rd. What is the approximate combined weight? So we're adding the weights together. All right, let's go ahead and add. In order to add anything in exponential notation, you have to have the same exponent here, or you cannot add. So if I have 1.44 times 10 to the 4th, and I want to add 7.94 times 10 to the 3rd, I can't add these because these decimals technically don't line up because of these. This is going to actually move my decimal over 4 places. That would move my decimal over 3 places, and then my decimals actually would not be lining up. These have to be identical. So I need to either make this be 10 to the 3rd or make this be 10 to the 4th. It doesn't really matter. If I want to make this be 10 to the 4th, then I'm going to move it over 1 decimal place. Hold on. So if I move this over 1 decimal place, it would look like this, 0.794 times 10 to the 4th power. I moved it over. To get it back to where it was, I would have to multiply it by 1 more 10. So now these two both have, so I've converted this to this. Now they have the same exponent. So now I can add them. I'm going to go 1.44 times 10 to the 4th, and I'm going to line up my decimal here. This is 0.794, and that is a 4. It looks like a 9. 0.794 times 10 to the 4th. Now I can add these two together. They have the same exponent. Now I can add them. Okay, the decimals are going to line up, so nothing's written here, so it's a 0. So I'm going to add those and get 4. 9 plus 4, let's see, that will be 9, 10, 11, 12, 13. And then 7 plus 4 plus 1, that's going to be 7, 11, 12. So that'll be 12. Bring down the decimal. And then 1 and 1 is 2. So here's my decimal form, and I still have that multiplied by 10 to the 4th power. Okay, you have to have the same exponent in order to add to line up these decimals. And then I am already in scientific notation. I don't have to move anything over. So this should be my solution. 2.23 times 10 to the 4th, and they just rounded to 2 decimal places. So this would work. Now let me just show you real quick. Had I chosen to convert the other one, and I did it the other way, and I'll undo this real quick. Hold on. Let me pause and undo. Okay, had I chosen to change this to 10 to the third, well, if I want to change this to 10 to the third, I'm going to move my decimal over one place this way. Okay, if I move it one place this way, I take away an exponent. So this would look like this, 14.4 times 10 to the third. And then that would match up this exponent. And now I can line up my decimals and leave this one the same. This would line up like this, 7.94 times 10 to the third. Okay, so now these have the same exponents. I've lined up my decimals. I can go ahead and add. There's nothing here. That would be a 4. 9 and 4 is 13 again. 1, 3. Bring down the decimal. 7 and 4 is 11, 12. So 1, 2. Bring down the 2, and then 2 and 2 right here. So I get 2.34 times 10 to the third. Now this is not in scientific notation, because in scientific notation, my first number here has to be between 1 and 10. And this 22 is too big, so I need to move this decimal over one place. And when I do that, I'm going to take this to 10 to the fourth. So this becomes 2.234 times 10 to the fourth, and I end up with the same solution. So either one you want to convert, just make sure at the end this number is between 1 and 10. So you may have to move the decimal over. When I move the decimal this way, I make the number smaller than it was, so I got to add an exponent. Remember, when I move the decimal this way, I make the number bigger than it was, so I have to take away an exponent. Okay, let's look at 12. And then number 12, which number is greater than 2.7 times 10 to the fourth? Now this is a little bit easy to figure out because of this exponent. Okay, 10 to the fourth means it has 4 extra zeros than this. If you want to write this in standard notation, you can move this over 1, 2, 3, 4 places to see what it looks like. So if I move it here, then I have to add 1, 2, 3 more zeros. It would look like this, 27,000. Okay, so 26,000 is obviously less than 27,000. What about this? 1.4 times 10 to the fifth. That means I'm going to add 5 decimal places. So I'm going to add 4 more zeros here because it's 5 decimal places. Even though this is a smaller number than this, if I have an extra 0, it's going to be a bigger number. This number looks bigger than this number, but it's to the -6th power, which means it's actually a really small number because I'm moving it this decimal way 6 times. That's a really small number because of that exponent. This is to the 4th power, and this is to the 4th power, so I can straight up compare these. Which number is bigger, 2.5 or 2.7? Well, 2.7 is bigger. So this number, if I write it expanded out, it's going to be 25,000 because I move it over 4 decimal places. 1, 2, 3, 4. Okay, 25 is less than 27. So this is the number where I have a bigger exponent. Even though I have a smaller number here, I have a bigger exponent. Expand this guy out. Move it over 5 decimal places. 1.4, if I move it over 5 decimal places, 1, 2, 3, 4, 5. So I'm going to add 4 zeros. This number is, if I write it out here, it's actually 140,000, which is bigger than 27,000. So that exponent is the trick. Look at all the exponents. Which exponent's biggest? That's going to be the greatest number. If you want, you can put this into exponential form by moving it over 1, 2, 3, 4 decimal places. 2.6 times 10, because I made this number smaller than it originally was, I have to make this bigger, 10 to the fourth. So I can see now straight up with the same exponent that this is smaller than this. So look at that exponent. Whichever has the biggest exponent is going to be your biggest number. All right, which value for 43,900,450 miles is the best estimate for this distance? Which one of these? Okay, well, this one's not even in scientific notation because the decimal needed to be moved over one place. However, let's look what happens. If we move this into scientific notation, the decimal goes 1, 2, 3, 4, 5, 6, 7 times. 4.3 times 10 to the 7th would be an approximate if I dropped off all of this. So which one looks best? Here I have something 10 to the 7th. This is 10 to the 5th. This is 10 to the negative 7th. It's not that. 10 to the negative 5th. It's not that. These are actually tiny numbers. This could be, if I moved over one decimal place, this would actually be 4.39 times 10 to the 6th, but it's not 10 to the 7th, so I'm going to have to go with D. 4 times 10 to the 7th would be the best approximation for this. So they approximated this to 4 instead of 4.3, but it has the correct number of decimal places. So they just approximated this to 40 million instead of 43,900,450. All right, let's go to number 14. A city recorded a total of 1.56 times 10 to the 5th hours that its citizens walked to raise money for charity. Which value expresses this number in standard form? So we just have to put this back into standard form. It's 10 to the 5th, so I'm going to move the decimal to the right 5 places to make it bigger. Okay, this means it's bigger, so I'm going to go 1.56, and I'm going to move it 5 decimal places. 1, 2, 3, 4, 5. So I need to add 3 more zeros. And if I write this out, it would be 156,000. Put your comma where it needs to be after every 3 numbers. And it would be C. Okay, let's go on to number 15. Estimate the root of 104 to the nearest integer. You did this in lesson, I think 4-6, where you're representing that to the nearest integer. This is a square root. It's not a perfect square, but I would like you to know your basic perfect squares. If I wrote them out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, just like the first 13 perfect squares. You should kind of know those just by seeing them, okay? So 1 squared would be 1. 2 squared, 2 times 2, 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared, 10 times 10 is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. So know these numbers, what they look like, okay? Those are your basic perfect squares. So what I'm going to do is I've written out several perfect squares. These are the integers. When I square root these, I get back to the integer. So if I square root 104, come over here to your perfect squares. There's 100 and 121. So 104 fits right in between those. Now, which integer is it closer to? Well, 104 is much closer to 100 than it is to 121. So when I take the square root of 104, it's going to be much closer to 10 than it is 11. So to the nearest integer, the square root of 104 is going to be about 10. Know your perfect squares. Figure out where that guy, the square root of 104, lies. It lies between these two numbers. So when I square root it, it's going to lie between these two numbers. Much closer to this number, so I pick 10. If I had a number that was closer to 121, I would pick 11. Now, if you want on your calculator to square root 104, go ahead. Go second square root 104 on your calculator, and it's going to give you, I don't know if you guys can see that on this calculator. 10.19803, or approximately 10.2. So you can see that's much closer to 10 than 11. All right, but know your perfect squares. Write them out like this if you need to. All right, on to the numbers. Okay, we went over the number system in the last chapter, the irrational numbers and the rational numbers. Look on page 174 of your textbook at that little chart and make sure you understand the number system. You have the natural numbers. The natural numbers is your innermost circle. That's 1, 2, 3, 4. Whole numbers is the next. It's those same numbers. They go on forever. It includes 0, 1, 2, 3, 4. And then from there, after you have your whole numbers, you have your integers, okay? So those would be the negatives, -2, -3, -4. It also is the positive. So it's these numbers, but including the negatives. You still have 0, 1, 2, 3, 4, and so on. They go in both directions, okay? So these are your naturals. These are your wholes. Z is what we use for integers. And then also in that, we have what is called rational numbers. Now your textbook, I don't know if they use R for rational numbers, but rational numbers are anything that can be written as a fraction. 1/2, 2 2/3, okay? 2.3 repeating can be written as a fraction. Repeating decimals can be turned back to fractions. Any decimal, 2.3, this can be turned back to a fraction, so it's rational. What is irrational? Irrationals don't repeat, they don't terminate, they go on forever and ever and ever. So irrational numbers, okay, are numbers like pi, okay, the square root of 3. This doesn't ever terminate or repeat. If I type the square root of 3 on a calculator, it's going to go on forever and ever and ever. That decimal goes on forever. It does never end. So I remember irrational is completely doesn't make sense. It goes on forever. It never stops talking. It's irrational. Think of an irrational person where they just go on and on and on. A rational person can be brought back to fraction form. So these are rationals. Irrationals are square roots of non-perfect squares like 3 and numbers like pi, 3.14, that goes on forever. So where's the irrational here? This is tricky. 5.3, that guy can be written as a fraction. It repeats. 5 6/7, that is a fraction, so it's not irrational. It can be brought back to fraction form. 7/3, not irrational. It's a fraction. This guy, this is the square root of a perfect square. If it was square root of 25, that's actually 5. That's a rational number. Square root of 26 is a decimal, goes on forever. It never repeats, it never terminates. So your irrational number, or the one that goes on forever, would be the square root of 26. Make sure you understand that. Irrationals are going to be square roots of numbers that are not perfect squares, okay? They go on forever, and they never repeat, and they never terminate. Those are irrationals. Okay, so let's go to 17. The diameter of Mars is about 7 times 10 to the 6 meters. The diameter of official regulation basketball is 0.45 meter. About how many times greater is the diameter of Mars than that of a basketball? We'll divide it out. If you want to know this times what is 7.6 times 10 to the 6, how many times greater is it? So I have to multiply this times something to get to there. Do the opposite. Divide it out to see how many times greater it is. So I'm going to take, and I'm going to go 7 times 10 to the 6, and I'm going to divide it by 0.45. Well, I can't divide these out like this. Actually, I could just do the division. It might be easier if I have times 10 to the something over here. You don't. You can just go 7 divided by 0.45, and then you have 10 to the 6th here. Let's go ahead and do that. 7 divided by 0.45, and I'm going to get 15.5 repeating. And then that's times 10 to the 6th power. Now, if I want to put that back into exponential form, or excuse me, yes, exponential form, I'm going to move this over 1 decimal place because this is too big for exponential form. I'm going to make this 1.5, and the 5's repeat, so I can put the repeat here. And then since I moved it over once, I made it smaller than it was, so I need to make this bigger. So this will be times 10 to the 7th. This is the approximate. How many times do I have to multiply this? I have to multiply this by 1.5 times 10 to the 7th to get to the diameter of the moon. That's a big number. Now, some students might turn this into exponential form by moving this over 1 decimal place, and you would have 4.5 times 10 to the, now I made it bigger than it was. Since I made it bigger than it was, I got to make this smaller than it was, times 10 to the negative 1st. If you want to do that, you can, and your division would look like this. Take this and divide it by this, okay? So it would look like this, 7 times 10 to the 6th, and you're going to divide that by 4.5 times 10 to the negative first. These are multiplied and these are multiplied, so I can just go ahead and divide straight up. If these were added, that would be different, okay? So I'm going to go 7 divided by 4.5. I'm going to divide these out, and I'm going to get 1.5 repeating, and then 10 to the 6th divided by 10 to the first. Remember, same base, subtract exponents. So this is going to be multiplied by same base. Subtract exponents would be 6 minus negative 1. Well, when I subtract the exponents, I minus a negative. A double negative becomes a positive. So this will be 1.5 times 10 to the 6 plus 1, 7. So I get the same answer as if I did it this way. If I just did 7 divided by 0.45, and it wasn't times 10 to the anything, so I just have 10 to the 6 up here. So I'm going to get 15.5 times 10 to the 6, and to put it into exponential form, I had to move the decimal over one place and increase that. Or I can put this in scientific notation immediately, then do my division, and then go ahead and subtract exponents. And I'm going to end up with the correct answer both ways. Okay. All right, let's look at number 18. Between which two consecutive integers does the square root of 41 lie? Once again, right amount. So if you know all your perfect squares, I need to know where does that fall in as far as my perfect squares goes. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. 6 squared is 36. 7 squared is 49. I'm going to stop because I know square root of 41 is between 36 and 49. It's right here. It's 41. So if I took the square root of 41, it would fall between the square root of 36 and the square root of 49. So when I square root 36, I get 6. When I square root 49, I get 7. So which two consecutive integers does 41, square root of 41 lie? It lies between 6 and 7. So write out your perfect squares and figure out where that one falls. And there you have it, guys. That is the practice benchmark. Go ahead and email me if you have any questions, and good luck.